this can be an atomic, right? So essentially you will do something like, I mean, in some, languages you have basically synchronized blah, blah, blah. And then the compiler will look at the block that says synchronized and then decide, what does it really need to do for that? Do I need to use a lock to do the synchronization? Or if it's just synchronized increment, variable a by 1, then it's going to think, oh, okay, so basically I don't really need a lock for that. I can just increment a as a single kind of hardware atomic primitive. So basically, you tend to have the programmer essentially do stuff in a kind of through the library or through the language constructs rather than write atomics directly and so on. Now, of course, in many of the languages, if the programmer does kind of use the atomics and stuff like that, it will be faster because there is only so much the compiler can prove, and also the library typically is kind of designed to basically offer popular constructs, not necessarily exactly the construct you need. Right. So it might be slightly more efficient, let's say, to use some sort of handwritten primitives of the kind of almost like assembler level primitives like atomics and synchronization of the kind of load link store conditional kind of style. But that's actually pretty rare because it's essentially we all write programs these days in high level languages. They all have these nice primitives and so on, and very rarely does it kind of pay off to optimize these constructs too much, as in you have to do a lot of work by hand, make probably a lot of mistakes in implementing these things, whereas the library writer, for example, for the synchronization library has already figured out how to correctly write this library given the consistency model and stuff like that of the machine. So basically, rather than kind of run the risk of kind of like make your own synchronization and kind of making synchronization primitives, basically like implementing a lock primitive is very, very tricky. So typically programmers are like really happy if they don't have to deal with that. Yeah, but it does pay to know about these things, because basically, like if you know that, for example, okay, what I'm asking the compiler or the library to do is something that can be done pretty trivially, that means your program will be probably pretty efficient. Whereas some of the primitives, for example, are not so efficient. One of the other things that's kind of important is like once you know how, let's say, a lock works and what makes the lock work well and stuff like that, you can say, okay, like for example, rather than try to optimize the lock implementation itself, for example, if you focus on kind of the main slowdown of locks typically is if you use too much serialization, as in you kind of keep the lock busy for too long and then threads have to wait for each other. That's probably going to cost you way more performance than basically you're creating a bottleneck, essentially, where kind of threads have this one thing that they have to wait for to go through one at a time, right? That's probably a lot less efficient than kind of a lot bigger efficiency problem than anything you can do in like kind of the library is costing me 50 instructions when I do a lock call. So in that regard, basically, the programmers really need to look at like kind of at the high level issue of pretty much, I am using synchronization. That means things will wait for each other. Let me figure out how to do this in a way that is correct, meaning I will use synchronization, but I will not implement them in such a way that it's basically, ending up not allowing the process to be used efficiently, as in they're mostly waiting for each other, right? So I think that's probably like the kind of the programmer's first task is that. Now, if you're writing a library primitive, and for pretty much every major development, for every major like kind of language library and for every major compiler set, pretty much you have people who are actually like specializing in that, basically just trying to kind of implement synchronization efficiently and yet correctly. Then you really have to understand what different architectures do, what are their consistency models, and which operations do they allow, which kind of assembler primitives do they really support, how are they supported in the hardware, as in, like is it really that this primitive is directly supported by hardware, or is it or in some sort of efficient way, or is it that this primitive really exists here, but the implementation is kind of clunky, it's really falling back on some sort of a software implementation that maybe less efficient. So that's kind of I mean, knowing these things, basically, like how things work and stuff like that, definitely helps, even when you're not really writing these library primitives. But one of the other things where it really matters is if you have a program that you've written and it doesn't have correct synchronization. So basically, the program is like misbehaving, essentially, like things that should have been serialized, for example, are not. And then I mean, understanding that like there is a consistency model, that things actually may not happen in the exact order you specified and stuff like that, really helps, because basically the failures of these programs are usually kind of strange for somebody who doesn't understand the for example, consistency models and stuff like that. I mean, as you have seen in consistency models, some of the more relaxed consistency models basically allow things that kind of a naive programmer would think just impossible, like this cannot happen, and yet it's happening. So somehow they start suspecting the debugger or something, like why is it reporting this cannot happen, but it can, right? So from that perspective, basically, when you're like debugging parallel code, it actually really helps to understand that, like, if you don't have synchronization that is synchronizing accesses, in what order can they happen, why they can happen that way, and the kind of what kind of synchronization I need to prevent that. Now let me go on to Michael's questions, which he kind of conveniently posted already too. So I'll go on the first one. Are we allowed to use more than one scratch paper to work on during the final? The announcement said you can only use one blank sheet. I would say let's stick to the one blank sheet. I mean, if you really need more than one sheet, I guess we can make an exception. But my experience is that basically having more than one blank sheet, you probably won't need that much paper. It's just going to be kind of like a clutter, essentially. So it's highly recommended that you don't, because you probably won't need more than one sheet of paper to solve the problems. But if you really want to, I think a couple of sheets is okay. I really don't want like somebody having like a stack of papers and then kind of shuffling them around and stuff like that, because then kind of proctoring that basically gets a little bit messy. There is a scheduled media maintenance for this Friday on Canvas. Will that interfere with the final? I'll check. If it does, then I'll see. I mean, if there is something that will actually affect the final, as in like it cannot be taken on Saturday and Sunday, let's say, then I'll definitely like extend the final period. If it's only like if it's only like a couple of hours or something like that on Friday, then just kind of skip that period. The reason why I scheduled the exam to kind of begin on Thursday afternoon and go all the way to like pretty much, I mean, in Atlanta, essentially starting like Thursday afternoon and ending on Tuesday morning, is so that basically students who work and cannot do the exam at work have the weekend to do it, and also students who kind of work but only have a reliable connection at work and can do the exam at work can essentially use the work internet either on Friday or on Monday to kind of give some flexibility. But it's not like you really need all 4 days. I mean, typically this exam would be like only 2 days. Really, this is more of a I'm giving you scheduling flexibility. That means that if there is only a couple of hours period, I mean, I'm not going to extend the exam for that. But if there is like a kind of the entire weekend is taken or something like that, then definitely I'll allow at least like a day more, so that students who kind of need to do the exam and it cannot be done on the weekend or something, have more flexibility to schedule it when they can do it. Okay, so I mean, I'll check exactly what the Canvas says once we end the office hours. Actually, let me do that now, just because it's so it's midnight. Oh, okay, so it's Friday midnight to 6 a.m. Yeah, so it looks like this is only for like videos and stuff like that, but kind of out of, just kind of as a precaution, basically, if you don't have to do the exam in that period, like try to avoid it. But apparently they don't anticipate any disruption to like the normal Canvas services. It's just that, I mean, it does have a video server and stuff like that. And apparently that's what's going to be, replaced. That's usually like a completely separate subsystem because it's for like video streaming and stuff like that. But if you don't have to take the exam in that period, then just do it in another period. Okay, so what's the difference between weak consistency and release consistency? Okay. I mean, for the exam, basically, this is more of a kind of fine point. As in, I tend not to ask questions that are going into details of that, but basically, weak consistency is typically, I mean, like what we treat as weak consistency is essentially when you have to say basically at what points in the program do you want to kind of sequentialize, right? So essentially, if I say something like load A, load B, and then like kind of serialize load C, that basically means that you can reorder A and B loads, but you have to finish both of them before you do the load C, right? So essentially, weak consistency has only one kind of memory ordering primitive, which is basically just like sync, and what it implies is essentially all of the memory accesses that were done. I mean, all of the kind of memory accesses, basically loads and stores, that precede the sync need to finish before any of the accesses after the sync can begin, right? And that's enough to implement all sorts of synchronization. For example, if you want to do a lock, what you will do is essentially you will, you will sync, and then you will actually to just lock. Basically, what you will do is essentially you will check the lock, and when you acquire it, you will sync and then do the accesses inside the critical section, right? Because what you don't want is to kind of reorder those and start, loading stuff from inside the critical section, and then when you are done with the critical section, you will sync and then release. And the reason for that is that you don't want anybody to see the release of the lock before your accesses before the source of the variable that you have been modifying are becoming visible to them, right? And then when you are when you're doing a barrier, for example, then you will again you will sync, and then kind of go into a barrier, and when you leave the barrier, you will again sync, right? So that essentially whatever comes before the barrier happens before the barrier, and then whatever comes after the barrier happens after the barrier for real, right? So essentially, weak consistency kind of does that. Basically, it's kind of weakening the consistency requirements by kind of having this like ordering primitive. Release consistency will basically has kind of two ways of ordering, right? One is acquire, which means basically you have to finish some things before you begin this, and the other one is release, which means basically like kind of don't begin anything until you're done with this. And if you do kind of like, I mean, essentially an acquire and a release together are what a sync is, right? Because like sync is essentially stuff before comes before everything, then sync, then everything after it. A release is more of a, you cannot reorder in one direction, but you can order in the other direction, right? So essentially the purpose of acquire is, to kind of, make sure that basically you have acquired, let's say you have acquired the lock before you access any of the variables inside, right? So essentially things that are after the acquire cannot come before the acquire, but things that precede the acquire are actually allowed to execute after the acquire in reality, right? So essentially acquire basically kind of, doesn't allow things to kind of go up above it, but it does allow things to trickle through it down. A release is the opposite, basically. It doesn't allow things to trickle through it down, but it does allow things that technically are after the release to come into the release. If you think of a critical section, you acquire a lock, you enter into the critical section, then you release the lock, and the acquire and release should be used when you acquire and release the lock, right? So the idea is that the stuff that is in the critical section, should not escape these boundaries, but the stuff before the critical section is allowed to actually happen inside the critical section, and the stuff after the critical section is allowed to happen inside the critical section, technically, as in like between the, so basically, you know, whatever you do in the critical section can be interspersed with stuff that follows the critical section. There is the reason for that is basically that stuff after the critical section should be stuff that is not to shared variables anyway. You know, if it were, then you should have put that in a lock too. So essentially, it's just allowing the processor to kind of have more scheduling freedom than a pure just like a single sync instruction. So essentially, acquire and release are kind of like directional. Let's say, you know, they only work in one direction in terms of the reordering. So they allow you to express more finely which orderings are okay and which orderings are not okay. A barrier, for example, would be both an acquire and a release need to be used for a barrier, basically, because essentially you cannot have stuff trickle through the barrier in any direction. I'm not sure if that answers your question, but I mean all of the consistency model, yeah.
Yeah, sort of. So though one of them is stricter. The release consistency is not as strict because it allows trickling through the critical section. But if you use weak consistency with 2 syncs, then there's no trickling in any direction.
Yeah. So basically, I mean, the idea is that essentially, if you're a programmer and you want an efficient program, right, you want the processor to be allowed to do any ordering other than the orderings you explicitly don't want, right? And the idea is that if you have sequential consistency, then you don't have to express anything, but the processor is not allowed to reorder much. If you have, let's say, weak consistency, then you know the processor is allowed to do whatever it wants, except at these boundaries where it's supposed to fully synchronize, right? But it turns out that for many synchronization operations, you know, you don't need to fully synchronize. You only need like specific orderings to be maintained. So you have, I mean, kind of the release consistency is essentially just saying in kind of what are you trying to prevent? Are you trying to prevent, you know, like I have a synchronization point, as in something needs to be ordered. Do you want stuff before the ordering point not to come after it, or do you want stuff after the ordering point to not come before it, and the two are distinct, right? So if you think of implementing a log, basically it's perfectly legal to do local stuff inside the critical section that is totally unrelated to shared variables, right? So essentially, if you think of it like a lock is acquired and then released, then inside the critical section, basically stuff that is around the critical section is allowed to come into it, but stuff that is in the critical section is not allowed to kind of get out of it, because then it wouldn't be inside the lock, right? So that's kind of the purpose of the acquire and the release, are just allowing you kind of a finer degree of control. Basically, the processor is still able to do like half the orderings it normally would for something like that. And then if you actually need something like a full sync, then you either have a full sync instruction too, or you have basically, and you need to do both an acquire and the release, right? And then you have other consistency models that are even more relaxed, as in they allow even more orderings and require even finer grain specification what do you really need. So for example, there is a thing called the lazy release, which essentially is kind of acquire and release, but you tell it which variables, you know, which memory addresses do you actually want ordering for. So it only will, you know, essentially it will say, I need you to complete accesses on A and B, and only then you can kind of proceed past this point. So basically, I need you to do both A and B before this point, right? And that's even finer degree of control, because now suddenly, you know, the ordering, like the, let's say, acquire that this thing is specifying, you know, only applies to the variables you listed. So suddenly it's not like an acquire operation anymore. It's an acquire and then parameters, as in like which variables and stuff like that. That sort of thing is really hard to implement in hardware, simply because you'll need an ISA, and you may need to have a huge list of variables and stuff like that. So typically, like hardware-based things are done kind of they stop at like kind of these you know, I mean, there are these memory fences basically that you can have an even finer degree of control, where you say basically acquire only for reads. So basically, writes are allowed to be reordered, but reads need to happen after this, right? Or so essentially, you don't allow, you know, you prevent reads from trickling up. Then you can have a, you know, so essentially you can have flavors of acquires and releases. That's kind of like some hardware, I mean, some ISAs have that, right? The lazy release is typically used in software implementations of kind of basically we are pretending to have shared memory while we actually have like parallel programs running on different machines, and they're using the network to maintain coherence, right? And then because it's expensive to send everything we've modified, you actually specified what needs to be sent pretty much by saying release A and B. And then what that means is when somebody tries to acquire A and B, you send them your A and B, right? You don't have to send them everything. So that's that's kind of the progression basically of kind of going from sequential consistency when you don't specify anything to essentially you have to specify the ordering, but it's kind of the full ordering to essentially not even all orderings need to be preserved when you synchronize, only some orderings, and you need to specify which, and so on. So basically what happens is each of these allows you to essentially give the processor more freedom to reorder things at the expense of having somebody at least reason about exactly what should be done. If you make a mistake there, your program doesn't work. Like, for example, and typically because in reality, programmers who directly use these primitives the hardware primitives are the library designers, typically it tends to work actually pretty well, because pretty much whoever writes the library probably kind of lives and breathes these things, so they actually know how to write a lot that uses even those like more obscure primitives. But that also means that like if you're trying to write some sort of a specialized synchronization primitive, like good luck with that, because even people with like years of experience just doing that will sometimes make mistakes. Okay. So there is could you go walk through the write throughput is different between RAID 4 and 5? Oh, okay. Okay, so let's begin with like RAID 1 and 0 essentially, and then go to RAID 4 and 5. Okay, so basically for if you remember, like RAID 0 essentially is not really redundancy. I mean, RAID 0 is pretty much meant for performance, and then RAID 1 is essentially redundancy with like some performance basically. So by having multiple disks, basically you can do two things, and you may get some kind of a little bit of both. One of the things is that you can use the disks in parallel, thus effectively improving what you can do in general. Like if I have requests that are going to different data that happens to be on the, let's say, two disks, then I can do them in parallel in some way, right? So RAID 0 is purely trying to exploit that, and essentially just says, okay, I'm going to kind of stripe the data pretty much. I'm going to kind of interleave blocks of data so that, a block is on disk 0, then disk 1, then disk 2, and you can have, as many disks as you want. And the idea is that when I do a large read or a write, or when I dependent reads and writes, chances are that a lot of them will be on different disks, which means that while one disk is reading A, the other one can read B, and I get basically, with n disks, I get the throughput of reading for n disks, and also I get the throughput for writing n disks, assuming that I have enough accesses to basically go to all the disks at once, right? So if you have a large sequential read, for example, that's easy to achieve, just because a large sequential read means that you're kind of getting a lot of blocks, and they're kind of strided, they're kind of interleaved such that essentially all the disks are used consecutively. So as long as you are able to recognize that, oh, this is like a 1 megabyte read, my blocks on disks are, let's say, 8 kilobyte. Oh, well, I can, just like, issue independent reads to all my disks and just get like kind of the first 8 kilobytes from each of the disks, put them in the buffer, the next 8 kilobytes from each of the disks, put it in the buffer until I'm done filling the buffer that was requested. RAID 1 basically says, oh, well, with RAID 0, you effectively get like the capacity of all the disks with the read and write throughput that is essentially the combined read and write throughput of all the disks, right? With RAID 1, what we do is we say, well, I'll keep all the data on all the disks. The usual way of using RAID 1 is essentially you have two disks doing this, right? And the reason, you can have any number of disks. Basically, you can have RAID 1 with like a pure RAID 1 with like 5 disks, which means essentially there is 5 copies of the data and stuff like that. Why we normally don't do that is simply because even with 2 disks, it achieves extremely good reliability, because essentially for this thing to fail, you have to have one disk fail, and before you repair that, the other one has to fail too, right? Which is already highly reliable, assuming you will repair the disk in a reasonable amount of time, because the disk typically has like, kind of average time between failures of like many years. And then what are the chances that even if you order it from Amazon and it comes tomorrow, what are the chances of the other one falling in that one day that you were unprotected, right? And then if you have a hot spare, which like in some sort of a corporate environment where basically there is like a site, there will be probably a spare on hand, because essentially you have multiple RAID ones kind of paired up like that, and essentially one spare will basically satisfy the whole, like in any given day there is a small chance that one of the disks fail. I can immediately replace it within minutes, and then again the whole thing is protected. So that's why RAID 1 typically is operated with only 2 disks, but in principle you can have as many disks as you want, right? And now the read throughput of RAID 1 is basically the same as read throughput of RAID 0, except except more powerful. The reason is that basically when I have reads to any data that I want, a copy of all of that data exists on all of the disks. So it doesn't matter how they're structured or something like that. If I have 5 reads, I can send them to the 5 disks if I have 5 disks. It doesn't matter whether, on RAID 0, the assumption is that if these 5 are on different disks, I can do that. Because data is on only one of the disks. Any given data is on one of the disks. So essentially, there is this requirement that the data actually is on different disks on RAID 0. On RAID 1, the data always is on all of the disks. So basically, any n reads can be read simultaneously from all of the disks. So essentially, you get like n times the throughput of a single disk always for reading. For writing, however, you don't. And the reason is that because you need a copy of the data on all the disks, when you want to write something, it has to be written to all the disks. So pretty much, if I do that by kind of just sending the write to all of the disks at the same time, essentially I'm using n times basically I'm writing n copies of the data. So essentially I'm getting the write throughput that is equivalent to one disk. If I had only one disk, I would have to write to one disk. If I have 10 disks, I need to write to each of the disks, but I can do that in parallel. So there is no loss in write throughput relative to what one disk can do, but definitely you don't get the benefit of having n disks as far as writing is concerned. It's essentially, it takes just the same amount of time to write the same thing to 10 disks as it does to just write it to one disk, right? So you lose the benefit of parallelism simply because all the copies need to be written. So that's kind of why for RAID 1, essentially the write throughput is the one that is affected. Now, if you go to RAID 4, what RAID 4 has, it has a parity disk. So basically, you have n disks. Let's call it n plus 1 disks because it's easier to talk about n being the data disks and the plus 1 is the parity disk. So basically, you have n plus 1 disks where n disks are for the data and the 1 disk is for parity. So now when we look at the read throughput, it's basically the same as RAID 0 except for the parity disk, right? So I'm reading the data from the n disks, whereas the plus 1 is not readable. It's useless for reading because it's a parity disk. It doesn't contain really any data that I can just like load and use in some way, right? So essentially, if I have like n disks, the throughput is basically the aggregate throughput of the n minus 1 disks, because one of the disks doesn't get any reads. It's the parity disk, right? Now, for writing, things are different. They're different in this way. In order to write to a RAID 4 array, I need to basically read the data, read the parity, and then compute the update to the parity, and then write the parity, the new parity, and the new data. Because basically, if I'm changing the data block, the parity needs to be changed too. Rather than, the only other way to update the parity would be kind of write the data and then read all of the n minus 1 disks and then update the parity by XORing them together. But it's essentially more efficient to kind of read the data and the parity only, and then basically you XOR the old and the new data. That's the change in parity, and then you XOR that with the old parity to get the new parity, and now you have the new data and the new parity, and you write them back. So essentially, in order to do a write to a single block worth of write to a RAID 4 array, you essentially need 2 reads and 2 writes. Assuming that the write and read bandwidth is the same, that basically means that essentially the latency of a write to a RAID 4 array is the latency of two accesses to the normal one disk. Why? Well, because you need to read the data and the parity. That can be done in parallel. Then you need to XOR things that can be done really quickly because it's done by the processor. So essentially that's not like, I mean, the disk is way slower than the processor. And then what you need to do is essentially write the two updates. So basically you cannot do, I mean, there are 4 accesses that need to be done, but they can be done kind of 2 at a time because the 2 can, so essentially the latency does increase, as in the single block write takes about twice as long, but it occupies 4 times the bandwidth that just a single write to a disk would take, right? So from that perspective, basically things look okay, because if I have a, let's say like a 4 disk array, but I'm using 4 times the bandwidth for every write, essentially that means that I should be able to effectively get the kind of when I'm writing, I'm getting the write throughput of a single disk. The trick is that if I distribute the writes across the array, the data accesses get distributed, but the parity ones don't. So essentially what happens is, if I try to do multiple writes to the array simultaneously, all of the parity updates for them, there is 2 per write, need to be serialized. So essentially the parity disk becomes the bottleneck, and effectively you have for writes half the throughput of a single disk for all the writes on the array. Simply because 2 accesses, one read, one write, to a single disk are needed in order to do the write update. And that means that single disk, essentially, for every write to the array, needs to do twice as much work that a single disk would need to do for a write to a normal disk, right? So essentially, the throughput of a RAID 4 for writing is basically half the throughput of a single disk. Okay, it doesn't matter that the other data disks can be done a lot in parallel. You have a bottleneck essentially, and that's what RAID 5 is trying to solve. So basically, RAID 5 essentially has the same protection as RAID 4. You can lose one disk, but the advantage it has, because it distributes the parity, is that every disk contains a little bit of parity and a lot of data. And what that means is that for reads now, I can distribute the data reads across all of the data disks, which is in this case all of the disks, not like n-1. Now it becomes n, right? Because every disk has some data. So if I'm kind of striping it carefully so that basically, let's say a large block being read sequentially will be supplied by all of the, let's say, 5 or 10 disks in the array, not like. So essentially, RAID 5 has a slightly better read throughput simply because it gets a throughput of all the disks, not of all but one disks, right? But the big advantage actually comes from when you do writes, because there are still 4 accesses that need to be done for every write, but now these 4 accesses are actually distributed across the disks, because if I'm reading data disk 0, I'm updating maybe, for that particular block, the parity is on some other disk. So essentially, the load of updating parity and data is now distributed among all the disks, which means that if I'm doing n accesses that are to kind of distribute, addresses that are well distributed, essentially, I'll need to do 4 accesses, but these 4 accesses will go for each access, for each of the reads, for each of the writes, I'll need to do 4 actual accesses, but they're going to equally share the load of that is equally shared by all of the disks, right? And what that does is essentially you get the write throughput of basically all of the disks aggregate throughput divided by 4. Essentially, they all share the load. It's just that the load of these writes is 4 times the load of what really would have been written if I didn't have this, right? So that's so basically for let's say, it's kind of like for a 5 disk array, essentially the read throughput is 5 times the throughput of the array. The write bandwidth is basically 5/4 times the write bandwidth of a single disk. And the reason is essentially that I get 5 times the bandwidth. It's just that I consume 4 times as much of it as I normally would, right? So that's that's kind of what the difference is basically. And the reason why almost nobody uses RAID 4 is because essentially it has like no advantage over RAID 5, other than it kind of simplifies things a little bit in terms of where parity is. But kind of computing this kind of round robin, for different blocks where the parity is and stuff like that is almost like a trivial hardware operation. So essentially, RAID 4 is more of a kind of stepping stone, essentially, when explaining how RAID 5 works and why we needed to kind of distribute the parity and stuff like that. I mean, nobody in practice really. I mean, you could use it in practice if you really, really want to have like a cheap, old, dirty, I mean, it used to be that basically that would maybe matter a little bit and you would save some money by having a RAID 4. But given how, sophisticated hardware nowadays is, and how much hardware you can cram into a disk controller, chip, it pretty much like it's a drop in the bucket having RAID 5 versus RAID 4 compared to everything else that usually a RAID controller will be able to do, which is kind of queue up requests, do stuff like for example plan for the head movement. I mean, usually this controller does like a lot more than just kind of do accesses the way you told it to do accesses. Like if it gets two accesses, or I mean, there is essentially scheduling of accesses so that basically I don't move the head too much and stuff like that. Like if I have accesses to kind of sectors on one end of the disks and then accesses to interspersed with accesses to the other end of the disk, basically the disk controller will actually make a plan for it and say, oh, okay, I can kind of start at one end of the disk and then as I move, I stop along the way to satisfy accesses. It doesn't matter in what order I got them. It matters just, kind of in which order I can, because that way I can only like move the head kind of in one direction once and do that. And there are all sorts of algorithms that essentially implement that. And modern disk controllers typically do that because, again, it's used to be that's like it's a highly sophisticated disk controller, but nowadays, again, compared to all the other hardware that we have in the system, basically the hardware of pretty sophisticated disk controller is essentially trivial. So that's why like you don't see RAID 4 anywhere anymore. It's essentially can tolerate the same number of disk failures, one, while having slightly worse read throughput and much worse write throughput. So who would ever want it?
Thank you.
Yeah, no problem.
Hello.
Yeah.
Yeah, I have a question about it has to do more with one second with directory-based coherence and MOSI coherence. And basically, in the videos, it was said that you can only use these two coherent systems up to 32 cores, because at that point, if you have more than 32 cores, both of them just are not as performant anymore, and you
Yeah,
just
yeah.
have to
Okay,
jump.
yeah.
So are we saying that any computer that we have today basically it's limited up to 22 cores.
No. I mean, what we were talking about is basically the limitation on like how many cores you can have is basically that if you have like a kind of like a snooping coherence protocol with a shared bus, then you are limited to basically what the bus can handle, right? Because essentially all misses, so each core will have some local caches, let's say level 1 and level 2 in modern processors. And then all of the misses in level 2 of all the cores will go through the bus to the level 3 cache, right? And the problem is that as you increase the number of cores, this aggregate throughput of all the cores will be basically n times what one core would have as far as misses are concerned. And the bus can take only so much traffic because requests, I mean, things have to go through the bus one at a time because it's a shared bus where only kind of one request can be made at a time, and one set of, like one block of data can be transferred at a time and stuff like that. So essentially the limitation to, kind of 8 to 32 is there because of the shared bus, not because of any inherent limitation of the coherence protocol itself. As far as the coherence protocol itself is concerned, as long as you can make a shared medium that is instantaneous. I mean, like if, for example, if I had like a perfect bus that allows me to just broadcast to everybody. Keep in mind that like snooping inherently requires, like the simplistic snooping, where essentially I see what others are invalidating, without any sort of directory, requires essentially that everybody sees all the requests, which means that essentially the traffic of all the cores needs to be seen by all the cores, and that means essentially that the throughput of the single thing that carries all the data is essentially shared by everybody. So with the bus, you have that problem, right? The bus can only take so much traffic. You can have a better bus. You can have the only way you improve the number of cores that can be attached to a bus is you basically get a higher bandwidth bus, or you make local caches bigger so that there is fewer misses generated onto the bus by the large number of cores, right? But keep in mind that as you improve the bus technology to become slightly higher bandwidth, as you improve the process technologies and fabrication technology to give you the ability to have larger caches, you are also improving the processors, the cores themselves, such that they are faster, which means that they do more accesses per second, which means that if you had the same cache miss rate in the local caches, they would generate more accesses per second on the bus, simply because 1,000 miss is done in half the time. 1,000 accesses with a, let's say, 1% miss rate is 10 misses. But those 10 misses with a faster processor are done over a smaller amount of time, which means you need a higher bandwidth bus to do that in that time interval, right? So essentially, the kind of the limitation, as in you cannot have a lot of cores on a bus. That's because of the kind of shared bus. With the directory, you eliminate that problem. Basically, you can still have like a messy protocol, except now what Messi fundamentally wants, which is to snoop on others' accesses, has to be, the snooping basically has to be regulated in some way. Like you don't actually get to snoop on everybody's accesses. Now there is a directory that essentially selects who gets the messages and stuff like that, so that essentially when I request something and it goes out, it doesn't go to everybody. It goes to the directory, and then the directory decides whether it needs to go to everybody or not, and most things don't need to go to everybody. So essentially, now I'm using kind of point-to-point, essentially, communication where, for something that I want, there is a directory somewhere, and something that you want, there is a directory somewhere else. Remember that the directory is distributed among the cores. So basically, the directories essentially share the load, so that essentially many loads can be, many misses can be done in parallel, simply because separate links are used from me to what I want, and from you to what you want. So basically, there is kind of this, now you're suddenly able to simultaneously use the bandwidth of multiple links, but for different misses. So that allows the number of cores to scale. So basically, the limitation, the reason for the directory is basically that it's a lot harder to do coherence that way from the kind of design perspective. But it's necessary if you want to have a lot of cores and if you want performance to be really good, because with a bus, before you totally saturate the bus, you start feeling the performance effect. So basically, when the bus is half busy, as in half of the time is occupied by somebody, you already start having, occasionally conflicts, as in, when I generate, like there are, let's say, 31 other cores. When my core generates a request, if the bus is busy half the time, that means that when my core generates a request, there is a 50% chance that that happens during the time the bus is already busy, which means that even when the bus is half busy, it already impacts performance because half of the requests have to wait at least some amount of time, right? And that's the problem really with the bus. It's not like the bus kind of cuts off at some number of cores. It's that basically the bus, with one core doesn't require any waiting. With two cores, you use only fraction of the bandwidth of the bus, which means that conflicts are relatively rare, but they are there. And then as you kind of increase the number of cores towards the kind of full utilization, basically you get kind of like a huge, pretty much exponential increase in it's kind of like the bus essentially kind of linearly, increases the weight slowly. But then when it starts approaching the full utilization, it basically balloons completely out of proportion. And that means that with a kind of large-ish number of cores, you already want to, you have a performance advantage from switching to something that is not a full, everybody gets everything broadcast medium. I'm not sure if that's the kind of what you're asking.
Yeah, okay. Yeah, I think I understand better. So
Yeah,
the bus is the bottleneck.
Yeah. So keep in mind that like the same messy protocol that we use on the bus is also used by the caches themselves with a directory. It's just that the directory is essentially, rather than I send a request out and it goes to everybody to snoop, my request now just goes to the directory who decides to whom to send the, let's say, invalidation and stuff like that. But as far as caches are concerned, as there is still the same messy protocol, as in they still observe things and adjust the state accordingly. It's just that they don't get to observe everything anymore. The directory is sort of mediating that.
Okay, so they're actually complementary, directory-based and messy.
It's just that it's a lot easier to explain messy on the bus, and also the first coherent caches were all on the bus because it's a lot easier to do that, right?
Oh, okay.
Yeah,
Okay.
But there is no inherent limitation in terms of like messy cannot do it. It's more like snooping with a bus cannot do it.
Okay.
Yeah. And there is no correctness problem there. It's just like it becomes an enormous performance problem essentially if you saturate or near saturate the bus band.
Well, if no one else is going, I'm gonna go for another question. That the topic of false sharing was very interesting because how do you protect yourself as a programmer?
Yeah. That's a very good question, and actually, false sharing is typically prevented by like the programmer essentially knowing that it can happen, right? So essentially, if you are trying to program you're trying to program something that will run in parallel, right? The idea is essentially, don't put data that will be independently maybe used by different cores next to each other in memory such that they may end up in the same cache block. So for example, a very good example is when you have people who do something like, I'll have an array of, let's say, counters, and what cores are going to do is basically, each core needs to increment a counter occasionally, right? And it's kind of like let's say I'm doing kind of like a counting, like a histogram of like there is a huge array, and basically I want to have a count of how many ones are in the array, how many twos, and so on. So what I'll do is basically I have the array. I now have a array of counts for every possible value, right? And let's say the values are only like 1 through, I don't know, 1,000,000, right? And then what I do is basically I want to split the work and do this in parallel. So the way this is done is basically you say, okay, core 0 gets the, let's say I have 1,000 cores, core 0 gets the first 1,000th of the array. The second core gets to count in the second 1,000th of the array, and so on. So that basically the array just kind of chunked, and each core gets like its own contiguous chunk of the array in which we are counting. So now the core will basically, each thread essentially will go over its swath of the array, and essentially for every element, take the value of the element, index into the array of counts, and increment that count, right? And they can do that in parallel. There is 1,000,000 counts, there is 1,000 cores, right? So basically the chance of the two cores wanting the same counter is really small, but it can happen. And when it happens, you have a kind of shared variable update problem. So you need a lock of some sort, right? So okay, so what we'll do is basically we will say, oh, this array is pretty large. The chance of actual conflict is pretty low. I don't need to have a lock for every element. I'll have a lock for like every, let's say, 10 elements or something, or 100 elements, right? So that essentially there is, let's say, 10,000 locks. So now you think, okay, there is still 10,000 locks. There is only 1,000 cores. Chances of conflict are pretty low, because basically, what are the chances of 2 of the 1,000 cores wanting the same lock, and a lot of that happening, right? Great. But then if you have a cache block and a lock is small, like a 1 byte, the problem is that there are 64 locks in each of the blocks. Let's say if it's a 64-byte block, so suddenly you don't get the kind of the diversity of having a 10,000 locks. You have really the diversity of 10,000 over, let's say, 64 or 128, depending on the block size, right? So basically, when you have something like that, essentially what you want to do is like don't keep locks that are kind of unrelated to each other in the same cache block. So typically, when you allocate a lock variable in most languages or most libraries, the library will actually allocate a whole cache block worth of stuff for that lock, even though the lock only maybe needs 1 byte. And the reason is that the designer of the lock library knows that it's a problem, because multiple locks will be used independently to protect different critical sections, but there will be ping-ponging between them just because of the locks being in the same block. Same thing also when you do something like, should I, for example, if I have fewer counters, what should I do, basically? Because again, like neighboring counters, although you can access them independently as in parallel, actually are gonna be in the same block, which means that if I fetch my counter and try to write it, and you fetch your counter and try to write it, you fetch it, you get it in exclusive state. I fetch it, now we both have it in the shared state. And that means that when one of us has to write, now it has to invalidate the other copy. The other one, when it wants to write, will then invalidate that copy and stuff like that. So basically, we're kind of ping-ponging this block, even though there is no real sharing of the data. So again, if you want to do something like that, basically, you either separate things so that basically each count gets its own cache block, or you try to do something, something else, like organize the data in such a way that you can maybe keep the counters more densely, but still ensure that like they don't tend to be shared by independent accesses from different cores. Another very common problem is, let's say you have a lock and the data it protects, and the data is pretty small and the lock is very small. So if you just kind of express it that way, and you kind of put the lock and the data into the same kind of array, it's a struct that has a lock and the data that it protects, it will end up in the same cache block. But the problem is that if this lock gets contention, as in if somebody is waiting for that lock, they're spin waiting on the lock, which means that essentially they have downgraded your block to shared from modifiable, which means that any accesses that you need to do to the data to write it will have to invalidate that copy. Then you do your write. Then they downgrade you again because they're spin waiting. So that and then so every single write will be a kind of miss-like thing that essentially needs to get the permission to write again, which is really bad from the perspective of performance, because not only do you have contention, which means threads are waiting for this thread to finish, it's also that you are slowing down the one thread that can free the lock, because everybody else is kind of taking away its permission to write. So again, if you have something like that, where there is like a busy lock, that lock needs to be separate from the data that it's protecting, because of the coherence issues and stuff like that, which is also again why the lock libraries typically will put a lock as a if the cache block is 64 bytes, the lock will be allocated as a 64-byte object, not and usually aligned to the cache boundary, to make sure that essentially nothing is kind of bundled together with this lock, because pretty much bundling anything with a lock, other locks or data that the lock is protecting, is a bad idea.
I guess
Yeah.
I guess it is a smarter idea just to use the libraries because many of them are already taking care of making sure that
I mean, for
descriptors are big enough.
yeah, I mean, for synchronization variables, yes, this was just an example that is kind of totally, easily explainable. But also, like if you have shared data, for example, if the pattern of accessing the data is, let's say, kind of, striding, like I access every fifth element of the data, and somebody else accesses, like I access elements 0, 8, 16, and so on, and somebody else accesses elements like 1, 9, and so on. That will create false sharing too, right? Because I mean, we're doing totally independent accesses, but item 0 and item 1 are actually in the same block, so we're having a lot of ping ponging when we're doing that. So basically, kind of stridedness as an interleaving of data that tends to be accessed by different things is also kind of a bad idea. And for that, it's probably much more efficient to reorganize the things so that each thread accesses like a contiguous block of elements that are packed together in a cache block, rather than do this, every element in its own block. Because if you do one element in its own block, you're essentially wasting cache space. You're fetching a whole block worth of data for essentially what could have been only like 4 bytes, right?
Okay.
Yeah. SMP and out of order wide issue. There is no like inherent advantage that wide issue has over false share on the topic of false sharing, right? I mean, out of order execution, essentially what it does is it allows you to tolerate delays in delivering. Delays in almost anything if there is independent work to do. So basically, in a typical program, there is some independent work to do, which means that you can tolerate delays, right? And like a large ROB, basically being able to kind of look at a lot of instructions ahead if you're delayed on something for a long time, definitely helps tolerate delays, right? So in that sense, out of order, execution with like a powerful core that can handle a lot of kind of look ahead is helping with any misses, per se. But you still don't want to have a lot of misses, because keep in mind that as you have a miss, essentially the out of order core will relatively easily find things to do for the next few cycles. And then slowly, like more and more things depend on the things it's been delayed on. So what typically happens is basically you have kind of like a kind of like a curve like this of kind of I start being kind of I have a miss and I don't even notice because I still have a lot of work that is independent. But as you progress, you're kind of running out of things to do, right? So essentially, having misses is never a good idea. The wider issue, I mean, the more powerful kind of core that is like a beefier core that has a larger ROB, a lot of reservation stations and stuff like that, will essentially kind of allow you to have a longer period of almost full activity after something like a miss, and a maybe slower decline for a little bit. But for example, like a last level cache miss, typically even the most powerful core will run out of stuff to do. Essentially, like if you have a 4-issue core with like let's say even like 200 ROB entries and many reservation stations, still being able to stay active for 200 cycles that it takes to maybe access the main memory would require like 800 instructions worth of busyness while waiting for something. And because the load that you are missing on will eventually get to the kind of kind of the to be the head of the ROB, and thus you have to commit that to proceed with committing anything else, which means basically when that happens, you only have, let's say, 200 ROB entries. That means there is only 200 instructions worth of look ahead that you have, which means you don't have 800. And that means essentially that, you can maybe tolerate 50-ish cycles even with such a core. In theory, in practice, it's less because, as you consume instructions that are independent, what you have left has less and less of those that are independent. So essentially, you're kind of, you start off with like having a lot of things that don't depend on the load that you're doing. either directly or indirectly. Like things that depend on the load are also unable to execute, which means things that depend on those are not able to execute, and so on. So pretty much you're kind of initially you have a lot of stuff that still doesn't depend on the load, but basically you're kind of every cycle you execute something, you are essentially consuming 4 of those. So very quickly you will not be able to find 4 anymore. You'll find only 3 or 2 or 1, and then finally 0, at which point you're fully stalled. And having a beefier processor kind of ameliorates the problem a little bit, as in it does help a tiny bit, but basically misses are still a problem. Also keep in mind that having these coherence misses and stuff like that, typically you're not going really off chip, so you can kind of tolerate some of them pretty well, as in they typically just go somewhere else on the chip. You can maybe tolerate like 20-30 cycles worth of delay with like you still don't run out of things to do, although you're kind of not able to run at full steam anymore. But there is also the problem of essentially energy consumption and so on. Keep in mind that like a miss that goes and does coherence actions consumes a lot more power than a miss that stays in the local caches, because the local caches are very small and the communication to them is local. So basically you kind of send a request to them for almost free, as in the sending of the request is almost free because the wires are short, and then it's a small cache array, which means it consumes little power to be looked up, right? When you send a request to the last level cache or to the coherence, to the bus, basically, if you have a directory, then it's basically there is a lot of power spent on just routing your thing to the directory. Then the directory needs to spend power to be checked, which is about the amount of power that the L1 cache will spend for a check. And then it needs to essentially either look up the data in the local L3 slice, which is way bigger and more power hungry than the other one, or forward the request further, which spends more power on routing, on messaging, basically, and stuff like that. So essentially, the amount of power consumption for any coherence request is usually like an order of magnitude, or like more than just an order of magnitude, higher than the cost of so basically, the latency is also an order of magnitude higher, but you may be able to tolerate the latency, but the power effect, essentially, you don't benefit anything from out of orderness. If anything, you are consuming more power in the cores too. So basically, you do want to prevent misses of all kinds, including like fault sharing and stuff like that, if you can. Not only for performance reasons, but also because they're extremely, extremely expensive in power. And nowadays, essentially, power is performance, because if you're consuming little power for the same amount of instructions, you can clock your processor higher, and it still won't warm up too much. If you, however, are consuming a lot of power, the chip heats up, and that means you have to lower the clock rates just to let the chip maintain its temperature. Otherwise, it will, pretty much, if you generate too much heat, the chip will burn out. And modern processors kind of translate that directly into a slowdown. So essentially, you don't have like, I'm consuming too much power. What you have is essentially the processor detects that you will consume too much power and limits the power consumption by slowing down. So essentially, the kind of doing power inefficient things pretty much amounts to like a slowdown in the end. Okay, so we have a time for basically like one more question, because I do have to go. I don't know why, but they have like a night discussion of some sort. So I do need to at least like show up for that. So if you do have like a kind of last question, or maybe two if they're quick, let's answer them. But like we'll have to end soon. Okie dokie. So there seems to be no questions anymore at this time. So good luck on the exam. Don't forget to take the exam. As has been pointed out, there appears to be like a maintenance thing going on Friday with the Canvas. What what I've been told basically is that like these kinds of things that affect essentially media streaming and stuff like that tend to not have any bearing on like the other aspects of Canvas. But just to be safe, if you are not like really, I mean, if you don't have to take it during that time, try to avoid it. Basically, I mean, just like out of abundance of caution, let's like try to avoid taking the exam at that time. It shouldn't affect things, but if it does, basically, and it's only like a 6-hour period apparently during the kind of more than 72 hours that we have for the exam. So you still have plenty of time like before and after that to actually take the exam. So try to just avoid it if you can, but shouldn't be a problem if you don't. Okay, so good luck, and I hope you all do well on the exam.